Okay, so this video is for Physics 11, continuing with our work on vectors, vector addition, vector subtraction, and this video is just going to be a couple examples of how we can then apply our formulas for calculating velocity using displacement over time to, we can apply those with the vectors that we've been dealing with, right? So there's not a whole lot of new stuff coming in, just trying to apply everything, putting it together, okay? So we're putting together the work that we've already done from Unit 1 on calculating velocity, right, by taking total displacement divided by total time, but this time kind of being given information about the vectors, and it's not going to be as easy as what it was in Unit 1 where we just were able to kind of graph it. It was just, north, south, east, west, and you could just draw a nice straight line and it worked out. Okay, so that's what this video is going to be. Okay, so again, so we're going to be using those vectors to determine the velocity. All right, so again, if we remember what we did in Unit 1, right, we had our formula for velocity being velocity is equal to d over t, where v is velocity, d is displacement, and t represents time. Oftentimes we would put like a little arrow over top of this d to represent that it is in fact a vector, so the direction does matter. All right, it's just kind of hard for me to type that in there. Okay, so when I do the notes on the whiteboard, it will have a little arrow over the top to indicate that it is in fact displacement and not distance. Okay, so what we're going to be doing is using that formula with other bits of information about vector addition or potentially vector subtraction to figure out the velocity of the object. Okay, so again, when we're doing that, we need to first find displacement. Okay, so like I mentioned in that little preamble, it's not going to be as easy as it was in Unit 1, right, where we were using graph paper and you were just able to kind of go up, up and over squares. This time we're again dealing with going at an angle and then having to draw the displacement and kind of figure out what's happening, okay? So in order to find that total displacement, right, that straight line connecting from where you started to where you finished, we need to be able to use those vector addition properties that we've been talking about, right? One, are we drawing them correctly? And then two, are we being able to calculate the values correctly? So we'll be going over two examples today. One is another example where we'll solve for the missing angles and missing displacements using our math principles of like law of sines and law of cosines, and the other one we will actually go over the vector components method again. Okay. Again, don't forget that when we're dealing with these problems, time is going to have to come into play. So making sure we're carefully reading problems, going over, okay, well, what amount of time has happened total? If we're being given speeds over a particular amount of time, then what we need to figure out is, well, what is the actual distance displacement travel so we can calculate total displacement, okay? And you'll see some of those examples in your worksheet. Right, so when we're talking about calculating that velocity, it's kind of the same general steps of what we've been doing before. So start with your vector addition and plot all sections of an object's motion. Okay, so plot the distances that it's traveling in each section. Draw your resultant vector, right? So from going tip to tail again, from the tail of the first one, right, from where you originally started all the way to where you've actually ended up, right? That's your resultant vector. Calculate that length and direction of that resultant vector using either vector component method or just math method using law of sines and law of cosines. The question, because we're dealing with velocity, is also going to give you some sort of amount of time, right? So once you've calculated your velocity, your displacement, to calculate the velocity, you need time that displacement occurred. So you will end up having to plug those two things into that formula where velocity is equal to displacement over time, and then get the value for your velocity and whatever it's asking you for, right? So it might be kilometers per hour, or it might be meters per second, okay? And then, of course, don't forget your direction and write your concluding sentence, all right, of what's happened in this particular problem. All right, so like I said, we're going to go over two problems today. So this one is the one where we'll do using the math version of trig with law of sines and cosines, but let's kind of go through this one together. So a family sets off on a journey and begins traveling 120 kilometers north 25 degrees west. After driving in this direction for 1.15 hours, they change course and travel 100 kilometers west 15 degrees north. If the second part of this journey takes 52.0 minutes, determine the family's average velocity in meters per second. Okay, so I've already worked out the solution. I've attached it here so you can kind of go over it just in your notes, but we'll go through this on the whiteboard now. Okay, so we start off knowing that our family is traveling for 120 kilometers at a direction of north 25 degrees west. Okay, so if we're going to set that up, right, we can again think about a north, south, east, west scenario here, right? That would be north and that would be west. And since we're going north 25 degrees west, we start north and we go 25 degrees towards the west. So we get something that maybe looks like this. Okay, again, if at home you have a protractor and you're wanting to try and do this as carefully as possible, you could do that. You could set up the protractor here and measure, 25 degrees back this way, kind of make a note, and then draw that there, right? So then what you have is that this angle in here is 25 degrees. You know that you've traveled 120 kilometers. All right, so that was the first leg of the journey, and that was for in 1.15 hours. Okay, then we get that the family changes direction and then travels west 15 degrees north. So again, if you draw your north, south, east, west bearing lines here, right, this time we're going west 15 degrees north, so we start west and we go 15 degrees in a northern direction, and we do that for 100 kilometers, right? So this angle in here is your 15 degrees, and that's your 100 kilometers, and that happened in 52 minutes. Okay, so that would be your drawing of your vectors, okay? And that should actually have an arrow because that's the direction, right? So again, we did tip to tail, right? Tip to tail, we're adding vectors here because we're trying to figure out total displacement. So our resultant vector would be from where we started to where we ended up, right? And that would be considered our displacement of this family's trip. Okay, so we need to now figure out what is this displacement. So we don't need to worry about the time just yet. Okay, so the 52 minutes and the hour 0.15 are not of concern right now because we're dealing with distances right now. So we need to figure out these angles, right? So again, using our wonderful angle properties, right? We know that this is 15 here, right? We know that this is a 90 right here. So what we need is, well, what's this angle here? Okay, and then we can add all those up to get this interior angle here. So if you think about it, your north-south lines are always running parallel to each other. So this creates an alternate interior angle theorem, or Z theorem, where this angle in here is going to have to equal this angle in here. So that's also going to have to be a 25 degrees, which means 25 plus the 90 going from the west, or sorry, so the south to the west, plus the 15, add that all together, and what you get in here is this 130 degree angle, okay, inside the actual triangle. Once you have that, you're able to set up your law of cosines because you have an SAS triangle, right, and you're solving for this value here. So you set up your displacement value squared is equal to the sum of these other two sides squared, right, so 100 squared plus 120 squared minus 2 times 100 times 120 times the cosine of that angle of 130 degrees. Okay, so that then becomes, please plug all of these things into your calculator and get a value. And that value that you get for the displacement squared is 39826.9. Right, and then you'd square root that. So your displacement would be like 199.57 kilometers, right? Or we could also put that back into meters because the question does ask us to give a velocity in meters per second at some point. So what we could do is take that and multiply it by 1,000 to get what it is in meters, right? So if we multiply that by 1,000 meters per 1 kilometer, we get that we're dealing with 199,570 meters. Okay, so we figured out the magnitude of the displacement. What we need now, though, is the direction. Okay, so obviously we know we're going some amount northwest. Okay, it's obviously more than north 25 degrees west. What we're basically trying to find is, well, either one of two things. You can either figure out what's this angle here, Okay, and if you can figure out that angle, you can say it's west, that angle north. Or if we figure out this angle and then add it to the 25, then we can get north that many degrees west. Okay, that's the option that I went for in the solutions that you're going to see. Okay, you are more than welcome to go for the other option to try and figure out that value, but this is the one that I did because I basically said, okay, I'm going to try and find this angle that's inside the triangle. Okay, so I'm going to erase this part and keep going here. So we try and find the angle that's inside the triangle. So now that I know this value here, I have my pair, so I can use law of sines. So I can set up sine theta over its opposing side, which is 100, is equal to sine of 130 over that displacement value. Now note that this was in kilometers, so I have to go back and use the kilometer value in order for this to be equivalent. So that's when I would use that 199.57. Okay, so I won't use the meters just yet. Okay, so multiply both sides by 100 there to get sine theta by itself. So you do sine 130 degrees divided by 199.57, then multiply by 100, and you get that that ratio would be 0.3838. You would then do sine inverse of 0.3838, and that would give you an angle value of 22.6 degrees. Okay, so that means that this angle in here is your 22.6 degrees. So our overall bearing or direction for this displacement was the 25 plus the 22.6, right? And that gives us 47.6 degrees. And that would have been measured from north going west. Okay, so at this point I could say that my displacement was we know that it's that 199.57 kilometers, and the bearing would have been north 47.6 degrees west. Okay, I technically only allowed 3 sig figs here, so this would actually have to round to 200 with just a decimal. Okay, but again, the question is actually asking us, what is the velocity? Okay, so kind of keep that in mind, right? Keep those values in mind, but we need to keep going. So we don't really need the diagram much anymore. But we know that velocity is equal to the displacement divided by the time. Okay, so our displacement was 199.57 kilometers. I've gone back to my non-rounded answer because I'm still doing calculations, and my final answer I will make sure that I round to my 3 sig figs. Okay, that's my value in kilometers divided by the amount of time, the total amount of time this trip took. So again, recall that the time value would have been 1.15 hours plus the 52 minutes. Well, those aren't in the same units, so we need to be able to put those in the same units. So what I could do is figure out what is 52 minutes in terms of an hour. I can do that by taking my 52 minutes, multiplying it by 1 hour per 60 minutes, or just taking 52 and dividing it by 60, and that gives you a value, I don't think I actually wrote that down, of 0.866 repeating hours. Okay, so 52 minutes is the same as 0.866 repeating hours. So our total time is actually 1.15 hours plus 0.866 hours, and we add those together. And we get a time value of 2.017 hours, right? So this can go up here. Okay, so our velocity is our displacement divided by our time. So this was the overall distance that we traveled, right? Well, not overall distance, but it's the shortest distance from start to finish, right? Displacement divided by the time it took overall to get there. Okay, so then we're able to take that value of 199.57, divide it by that value, and what you end up getting is this value of 98.96, just double check my work here, yeah, or 98.94 kilometers per hour, okay? But the question did ask for that in meters per second, so remember our little trick there where all we really need to do is take our 98.94 kilometers per hour, and if we're going to meters per second, we divide by 3.6, right? And that gives us our value of 27.48, but using sig figs, we only get 3, so 27.5 meters per second. Okay, so our average velocity, right, so our final kind of concluding sentence is that the average velocity is 27.5 meters per second. And remember, velocity is a vector, so not only does it have magnitude, it also needs direction. And the direction of the displacement is also the direction of the velocity, which was our north 47.6 degrees west. Okay, so that would be your final answer in that question, right? So there's just we're just adding to it, right? So everything we've done so far has been just well, this is how we add vectors, and this is all the stuff of how we would find the displacement. This is how we subtract vectors. This is how we would find the change in something, right? One thing minus another. Now we're going back and connecting it to, well, what about if we needed velocity, but we were only given values in distance, right? So we'll find the displacement divided by time, and away we go. Okay? So that's that first sample problem. Again, if we go back here, you will notice in my notes I did it slightly differently when I kind of wrote it out. You do still get those same angles there. You still get the same velocity, but what I had done was I'd taken my value in meters and I converted my hours into minutes and into seconds. So instead of getting it in kilometers per hour and dividing by 3.6, another way you could have approached this was turn your kilometers into meters, figured out your time, taken your time, turned it into minutes, turned it into seconds, and then gotten your velocity by doing meters divided by time in seconds. You get the same value, right, of the 27.5. Okay, so just there are other ways of approaching this. Do the one that works for you. Okay? All right, so now we have sample problem number 2. So this is the one where, again, I'm going to review how we do the vector component method because the thing with this question is that it has more than 2 steps, which means we don't actually make a triangle, which makes things a lot more complicated in terms of, we can't use law of cosines when it comes to non-triangular shapes. So vector components might actually be easier here. Okay, so with this one, we kind of read it out. What ends up happening is we start by going 8 kilometers, because the motorboat begins an afternoon voyage by first traveling a distance of 8 kilometers south, right? It then shifts directions and travels 11 kilometers east, 11 degrees north, okay? And then finally, the boat travels 6 kilometers to an island in the direction of 35 degrees east of north, right? Or you could also write that as north 35 degrees east, right? Because you're starting at north and going 35 degrees to the east, right? You're going east of the north, okay? If the journey takes 35 minutes, determine the boat's average velocity in both kilometers per hour and meters per second, okay? So again, that average velocity would be your displacement divided by time. Okay, so step 1 here is we need to be able to draw this scenario. So back to the whiteboard we go. All right, so step 1, we go 8 kilometers south. So if we start here, we go 8 kilometers straight down. Right? We then go 11 kilometers east, 11 degrees north. So if we're thinking about that north, south, east, west plane, right, you're starting at east and going 11 degrees to the north. Okay, so you're doing this, right, where this angle in here is 11 degrees. This whole side length here is 11 kilometers, right? Then you're going 6 kilometers north 35 degrees east. So again, if you drew your north, south, east, west, so starting at north, going 35 degrees to the east, right? And you get that as your 6 kilometers, knowing that that's a 35 degree angle in there, right? So overall, your resultant vector, start to finish, does this. Okay, so it's a little bit south, but a lot to the east. Okay, so like I said, we don't have a nice law of cosines that we can do here. So instead, what we do is we use that vector component method and break each step into its x and y components. So in step 1, what we did was we went 8 kilometers south. So think about that in terms of a triangle of going x and y, right? Well, in terms of x, it did nothing. It did not move either left or right, okay? If we think of it in terms of the y values, right, where did it go in terms of up or down? Well, it went 8 kilometers down. Okay, so 8 kilometers, I'm putting that as a negative. All right, so those ones are nice and easy, pretty straightforward. In step 2, we went on an angle. So if we just drew the step 2 vector, what you get is something that looks like this, right? Where this is 11 kilometers, okay? And this was a triangle where the 11 degrees was here. And we're trying to figure out, well, how much did it actually go over, right? The x component, and how much did it go up? What's the y component? And when you do that, you create a nice little right angle triangle just thinking about that one single vector, okay? And then you can solve it using your basic right angle trig, right? Your sine, cosine, tangent. So for your x, you're solving for the adjacent side and you have the hypotenuse. So you can set up cos, right? So cosine of 11 degrees is equal to x divided by 11. You rearrange that and you get that the x value is equal to 11 times cosine of the 11 degrees. You put that in your calculator. That's not 11 squared. Okay, so this is the x2 value. Okay, so you multiply that together, you end up getting a value of 10.8 kilometers. And that again was to the east, which we would consider a positive value. To solve for the y value here, okay, this is the opposite side length. Okay, so that's opposite, and you have the hypotenuse. So that's a sine ratio, so you'd be able to set up sine of 11 degrees is equal to y divided by 11. Multiply both sides by 11, so what you get is that y2 is equal to sine of 11 degrees multiplied by 11 kilometers. And you do that, and you get a value of 2.10 kilometers, and that was to the north, so that would also be considered positive. Okay. Finally, we go on to the third vector, right? So this the third step in the journey. Okay, so this one did the 6 kilometers north, 35 degrees west. So if I just draw that vector, give myself a little bit more space here. Okay, so if I just draw that vector, kind of looks like this, right? This value is 6 kilometers. The angle that I have is that this one here is the 35, but because I want to be able to draw this as a nice right angle triangle where this is my x component and this is my y component, right? That's x3 and that's y3. The 35 degrees is not inside the triangle, but it would be complementary. So just 90 minus 35, and that gives us a value of 55. Okay? The reason I'm doing this is so that it's consistent, so that every time you do this, when you're solving for the x, you're using cosine, and when you're solving for the y, you're using sine, okay? You can set up your triangle that looks like that instead, and you can use the 35, but then you would be using cosine to solve for y and sine to solve for x. If you're fine with switching it up, I'm cool with that, okay? But just you have to be confident that you are not going to mess that up, okay? What I'm trying to do is set it up in such a way that you're being consistent with which trig ratio is used to solve for which component, right? But mathematically, you will get the same answer as long as you're either A, switching your angle correctly, or B, using the right trig ratio. Okay, but this is essentially the triangle you get, so that you get the same type of setup. We're solving for x as an adjacent side length, and you have the hypotenuse. So x3 is found by taking cosine of 55 degrees and multiplying it by the hypotenuse of 6, and getting a value there of 3.44 kilometers. And again, that was to the right. So that was a positive value. And then the y value, again, is going up, and it's the opposite side length with the hypotenuse given, so you can use sine there. So y3 will be found by taking the sine of 55 degrees and multiplying it by the 6. and that gives you a value of 4.91 kilometers. And again, that's in an upwards positive direction. Okay, so that's just finding the vector components of all three steps. Okay, once you have all of those, you then go for the sum, the total vector component, the total x and the total y. Okay, so if I do that, what I now do is I take the sum, right, so that's our symbol for sum. The sum of the x's is going to equal x1 plus x2 plus x3. So when you add that together, 0 plus 10.8, because it was a positive. And then x3 here was again a positive 3.44, so plus 3.44. Okay, so the sum of your x's all together ends up equaling 14.24 kilometers. Okay, so overall you've traveled 14.24 kilometers to the east. Okay, and then you take your sum of your y's. So again, that's y1 plus y2 plus y3. So looking here, this was 8, but it was in a southern, so a negative direction, so it's negative 8 kilometers. And then we have a positive 2.1, so plus 2.10 kilometers. And then y3 was 4.91, and again, it was a positive because you were going north, so plus a 4.91 kilometers. So if we add all those together, then what we get is an overall y distance of negative 0.99 kilometers. Okay, so overall, we've gone 14.24 kilometers to the east and 0.99 kilometers south. Okay, so now we can draw that updated right angle triangle. Right, so like I said, overall, from start to finish, we've gone a total of 14.24 kilometers to the east, and we've gone a total of 0.99 kilometers to the south, and this would have been our resultant vector, right, from the original diagram, right, which kind of makes sense, right, because we did go overall a bunch east and then a little bit down. Okay, so this would end up being our displacement that we're solving for, and that's just a nice little right angle triangle, so we can solve for displacement not using law of sines or law of cosines, but just nice Pythagorean theorem, right? So your displacement, if we just rearrange your Pythagorean theorem, right, this squared plus this squared, and then square root it, okay, do all that, plug that into your calculator, and you end up getting a value of 14.3 kilometers. Okay, so now we have the displacement, but we also need its direction. Okay, so again, if we can solve for this angle in here, that's east, whatever this angle is, south. Okay, and again, because we have the opposite and the adjacent side length, we can just use tan to solve for that angle. So the angle of theta would come from tan inverse of the opposite divided by the adjacent. And remember what I told you when I first started teaching this type of method of doing this. When you're doing this, only use the absolute value. Don't worry about whether these values are positive or negative. Just use the positive values to get the right angle, and then you put the direction in yourself. Okay, so this would then be opposite, so just use the positive version of 0.99 divided by the adjacent, so 14.24, right? And we tan inverse that value, and what you get there is an angle of 3.98. Let's call it a nice 4. All right, so you get that value is 4 degrees. So going back to the overall point of this problem is figuring out, well, what was its velocity? Okay, so velocity, average velocity, is the displacement divided by the time. Okay, so these two things we definitely still need, right? And that was 4 degrees going east, 4 degrees south. Okay, that was the displacement. So to find our velocity, velocity is equal to displacement divided by time. The displacement is 14.3 kilometers. The time was 35 minutes. Okay, so the question asked us to give it in kilometers per hour as well as meters per second. So again, to get your 35 minutes into hours, you can just divide by 60, right? Because there's 60 minutes in an hour, and you get a value there of 0.583 hours. So displacement divided by time, right? That gives us now an average velocity of 24.5 kilometers per hour, okay, in the direction of east 4 degrees south. Okay, and our other option that it asked us for was what was it in meters per second. So again, you can just take your value that you got from kilometers per hour and divide it by 3.6 to get your values in meters per second. And you end up getting a value there of 6.81. Right, and then that again was at that east 4 degrees south. Okay, so those are your two values. I think just kind of looking back at this, what did we have that we were allowed to use for sig figs? So I should go back and double check that. 1, 2, 1, 2. Okay, so we do need to make a slight edit here because we only get 2 sig figs. So that being said, our velocity, right, will need to be changed to just 25 kilometers per hour. Okay. When we did this, it was 3.98, which means we would have rounded it up to 4 anyway, but it would just be 4.0 if we want to write it correctly with the sig figs. And then for this with 2, we'd have to get rid of that 1 and just have 6.8, and then still write this with 4.0 degrees. Okay, and then that fixes our sig figs, right, because we only get 2. Right, so there we have the vector component, right? So then your concluding sentence would be average velocity right for the trip is 25 kilometers per hour east 4 degrees south, or 6.8 meters per second east 4 degrees south. Okay, so there's the 2 ways of being able to do that. Okay, again, I had that solution out there as well, so if you don't want to have to re-watch the video and pause it, you can just kind of look at the sheet that I've kind of typed up there. I did forget to fix my sig figs here, but you now know about that. And that's all for this video. Okay, so again, it's not a whole lot of new material, it's just combining material I've already taught and putting it together in one lesson. Okay, so what you've got is a worksheet that has 5 questions, similar to the 2 that we just did. Okay, in those questions, if I just double check, there's one there that's actually pretty straightforward. You just need to kind of figure out, just the velocity. You were given displacement and time, because there's only one step. And all of the other questions can all be done using either just Pythagorean theorem or using law of sines, law of cosines. You don't have to use the vector component method if you're still not comfortable with that. However, if you would like to practice it that way, you will also be able to get the same answer. We're going to have a separate lesson later next week probably, just focusing on the vector component method and showing how it's useful in other situations. Okay, so work on the worksheet, those 5 questions, check your solutions. If things are not making sense, if you're getting the wrong answer, or if you're just not even sure where to start, please email me. I will help you as best as I can. Or if it's just even too hard to type out, just email me with a request for a Google Meet session and I will go live for some live office hours. Okay, to try and explain it in person. You can ask specific questions. Okay, and that's it.